Fasco facts manual, and I highlighted a bunch of this so we can touch on certain points. So I'm going to kind of flip through it and find those highlights, and anything I see in that's interesting, um, I'll note that too. But basically, everything on these first couple pages, we got tables of contents. So it goes through the introduction on that first page. It talks about power supplies, frequencies, motor types, motors, frames, enclosures, thermal protectors, lubrication, capacitors, drain plugs, stacks and windings, horsepower, load factor, mechanical characteristics, motor speed, high slip motors, rating motors with BTUs, which is interesting, cooling motors, how they're cooled, motor temperature, speed controls, removing motors, motor replacement, motor selection. I mean, on and on. I'll stop boring you by reading the rest, but it goes through a lot of stuff. It's like a 50-page guide. It's made to be a pocket guide. I've never actually seen the pocket guide. I've always found it online, but it's supposed to be a little pocket guide, so you can just carry it in your truck or something and look at it in case you got questions. So different power supplies for motors. This should hopefully be pretty easy right now. But anyway, you got single phase voltages, which can be 115 to 480, three phase voltages, 208, 460 basically. Generally, we'll be dealing with 208, 460, 240 single phase, 208 single phase, or 115 single phase. Um, I'm actually surprised they don't list 277 in here. Yeah, I'm actually surprised for some reason they don't have 277. Unless I'm really having a brain fart, you can have a 277 single phase motor too. So that might have just been an oversight. Um, 460 single phase would be interest. Well, no, because permanent splits that are 277 are generally 460. So that's right. But you can still have a 277 to neutral motor. I've seen them on water source heat pumps. All right. Some older motors will be stamped 220 volts. In this instance, a 208 or 230 motor can be substituted. That's pretty much true of anything that's a 230 volt motor. If it's 230 volts, it's good for 208 or 240. So that's just hopefully that's common knowledge for you. But if it's not, see right there, they list 277. But anyway, hopefully that's already obvious. All right, so frequency in the US is 60 hertz. Frequency in Europe is 50 hertz. If if you want to use a motor that was made for 50 hertz here, or you want to use a motor that was made for 60 hertz over there, it actually can be done. There's interesting information to be found about using motors made for different frequencies in different areas. It's outside the scope of this class. But if you ever see an engineer do something weird and pick a 50 hertz motor for use in our area, you want to double check that they didn't mess up, but it actually can be done. It's not that big of a deal. The power curves, the way motors work, they can deal with different voltages and stuff pretty well. So depending on the situation, a motor that's made for something else may be good for a particular application. So just an interesting tidbit to keep in mind. All right, so the most common ones are permanent split capacitor and shaded pole. I would say the next most common, if not actually more common than those, just because industrial use, would be your three-phase motors, which we'll talk about a little bit. Generally, they look really similar, but they're actually pretty different. So a shaded pole motor is used where low cost and low starting torques are required. They're used to drive blowers, bathroom ventilators, range hoods, attic ventilators, downdraft blowers, fan cools. Typically, where you're going to see them are inducer motors, bathroom ventilators, attic ventilators, and your range hoods and stuff like that. So basically, anytime you don't have a capacitor on a motor in HVAC and it's not three-phase, it's probably going to be a shaded pole motor. So a shaded pole motor can be recognized by the readily identifiable individual stator coil windings in the single copper band shaded coil formed around one side of each stator pole. So basically, a shaded pole motor just uses one main winding, and it's got a shaded coil that's around each stator pole, and that's what gives its rotation essentially. So instead of having a start and a run winding, you just have a single winding. The shaded poles aren't even connected to power. They're just there to mess with the magnetic field, essentially. So shaded pole motors rotate towards the shading band. We have capacitor start motors. You'll see these sometimes on smaller stuff where it's got the start capacitor built in. It could be a run capacitor built in, and I want to say that's more common, but I can't say I opened up these capacitors enough to tell you for sure. But you can have capacitor start motors. Typically, those are going to be like OEM specific applications. Um, but I'm going to basically skip capacitor start because I don't see them used that often um, as far as things that we need to replace on a regular basis. Permanent split capacitor is your next most common that you see in the field. Well, probably your most common you see in the field if you do residential, your next most common if you do industrial, commercial. But permanent split capacitors are used where higher starting torques are needed than what a shaded pole motor will provide. They're used where higher efficiency motors are required. So I'll talk about this again, but your shaded pole motor is about 30% efficient, somewhere in that range. Could be 25, could be 35, but it's somewhere around 30% efficient. Your permanent split capacitor motor is going to be probably 50 to 65% efficient, usually floating right around 60%. So they're not very efficient motors, which is why we're kind of moving to ECM a lot. You can get an extra 20% or so efficiency out of an ECM motor, but it's still double the efficiency, right, of a shaded pole. So it's much more efficient. It's funny if you follow like sump pumps and things like that people put in their basements. They just started probably about 5 years ago moving from shaded pole to permanent split capacitor motors in a lot of those pumps. So they're just now using the higher efficiency motor now in that application. Whereas in HVAC, we've been using them for blowers and stuff for a really long time. It's just interesting. But due to their efficiency, as they become the motor of choice versus the shaded pole, they are used to drive blowers and other air moving applications where shaded pole motors are found. They are also manufactured at higher horsepower ratings than what can be found in shaded pole designs. Therefore, they get used in heavier duty applications such as outside condensers. PSC motor can usually be recognized by the capacitor that is connected to it. Also, between the main pole windings and the motor, there are pole windings of finer wire. These are auxiliary windings. So you'll see a lot of the times people will call them auxiliary windings instead of start windings. So when you see that term auxiliary winding, they're talking about your start winding, if that's the terminology you're used to using. You have split phase motors. They're higher starting torque than a PSC. I can't think of a situation in which I've seen a split phase motor used. So I'm not 100% sure where I could give you practical applications of where you'll see that. Um, it says they have a narrowly set RPM range. So they're basically motor poles dictate your RPM. So they're basically, what is this? See if I can remember off the top of my head because I'm not that good. But basically, they've only got, I think, that would be 4-pole or a 6-pole range, if I'm remembering right, without doing math. But anyway, they don't have a very wide range of speeds, and they don't have the range of multi-speeds that you can have in shader poles or PSCs. I can't think of somewhere where I've picked one up. So if you're familiar with seeing split phase motors somewhere, more than welcome to butt in and tell me where. But I don't really see them. And then you have 3-phase, which of course, if you do any commercial at all, you'll see all the time. And it's the most efficient general purpose motor. So 3-phase are generally in the range of 75 to 95% efficient. 3-phase motors are really efficient for a motor. And they're used in industrial and large commercial applications where you have 3-phase power. And basically, you can set them up for high starting torque. You can set them high, but you can set them for high speeds. They can be designed in pretty much any way that you need a motor set up. All right, motor frames. Motor frame is a designation that a motor manufacturer assigns to a motor to describe certain construction parameters. Basically, the motor frame is going to is going to tell you a ton of information on a motor. So if you've never ordered a replacement motor for something, you will find that just the frame size can tell you a ton of information. Richard asks about how to make sure a three-phase motor is spinning the right way. We'll get to that in a little bit. All right. So anyway, the motor frame itself can be generally with voltage, phase, and RPM. The motor frame will give someone like an electric motor specialist or somebody like that most of the rest of the information they need to order the motor. It gives you the mounting characteristics, the shaft diameter. A lot of times I think it actually includes the how it's cooled. The motor frame is an important piece of information on the sticker if you're trying to get a replacement motor. If you don't give them the frame and they mess something up, you could end up with a motor that does not even fit what you're trying to put it in, because even though it can have all the other same characteristics, it won't mount right or something. So that's what really frame boils down to. So frame types are C-frame for most of the smaller motors that Fasco makes. And our most common one is going to be this 5.625 inches. A lot of times you'll see it listed as 5.6. So that's your blower for residential. Those are your blowers, your condenser fan motors, things like that. That's what they see the most. These are still pretty common, but we still see that 5.5 and 5/8 inch motor basically the most. So you, like I said, you'll either see that listed at 5 and 5/8, 5.625, or 5.6 inches. All right, they go through shaft orientations. Not that big of a deal, really. Most of our motors are going to be multi-orientation. You're going to be able to flip them if you need to. If you're getting an OEM motor, these things are relatively important. But the shaft orientation is just it's shaft up or it's shaft down. Nothing crazy. Motor enclosures. I don't want to get too deep into these because I feel like it's it's not that important for you to be remember all these abbreviations and things like that. But basically, you're going to have totally enclosed non-vented motors. Typically, something like a condenser is going to be that. The only way that it's cooled is the air blowing over it. So if the air around it's super hot, this thing's going to get super hot. There's not much ventilation. Well, there's no ventilation, right, in the motor. That's basically your condensers, your outdoor motors. Open motors are generally your blowers and things like that. You have lots of ventilation in it. So there's your open. Totally enclosed fan cooled is the same up there, but it's got a little a little fan built into the rear shaft so that it helps cool it. You got open drip proof. That's what you see most often in commercial blowers and things like that. They'll be open drip proof, so they've got a lot of ventilation, but they don't have any ventilation at the top. So if any condensate or anything starts dripping down, it doesn't actually get inside the motor much. Motor bearings. Motor bearings are important. It's not very complicated subject, but it's a relatively important subject. So the most common bearings are sleeve bearings. You're basically going to have sleeve bearings or ball bearings in most of your motors. Your big ones are going to be ball bearings. Your smaller ones are usually going to be sleeve bearings, but there's limitations to sleeve bearings here and there. So if you've never take one apart, I was hoping to put together some pictures, but I didn't get that far. But a sleeve bearing is basically just a round sleeve that fits on the motor, and then what they do is they pack um, cellulose or some kind of fiber up around where the sleeve bearing is, and they fill that with oil. And as that spins, it basically gets the oil to get on the shaft and keep the bearing lubricated. And that's going to dry out over the years. So those permanently lubricated motors, it just means it's a pain in the butt to relubricate. You can relubricate them. It's not that hard to take it apart and drop some 3-in-1 oil or something in there and relubricate it, so the bearing would last a lot longer that way if everything else is designed well and it's a good functioning motor. The thing is they're so cheap compared to the cost of removing that motor, taking it apart, lubricating that surface, putting it all back together and putting it back in, generally you're better off just replacing the motor, which is why they're permanently lubricated these days. It's the costs of the motors have come down so much, it's not worth relubricating those. Your bigger ball bearing ones, though, you grease those because those things aren't as jelly bean as your small sleeve bearing motors. Ball bearings are made with hardened steel balls held in between grooved inner and outer steel races. Ball bearings are used when heavy radial side thrust loads are encountered, such as a belt-driven application. Again, your commercial motors are almost always going to be ball bearing. Um, the ball bearings, there's actually different types of ball bearings. So you have, can I remember the terms? You got sealed bearings. You got like partially sealed bearings to where they're not completely sealed, but it keeps out dust and stuff like that. And then you'll have open ball bearings. Our bearings are generally sealed or at least have dust covers, but if you want to get into a rabbit hole, you can go into different ball bearings and things like that and learn about the different types because, our pillow bearings and things like that, it's kind of nice to understand what that bearing is and what it's all about. So we're not going to get that far into ball bearings tonight, but it is an interesting subject to educate yourself on if you have time. Um, so, um, They talk about Babbitt line steel back sleeve bearings are quiet, long life bearings capable of operating heavier direct drive, air moving loads. Basically, sleeve bearings are really simple. Okay, they're really simple. There's not much to them, but they're very quiet and they can last a really long time, just as long as a ball bearing. So it's not like they're cheap, and that's a huge issue. It's not like they just put in a crappy bearing because it's cheap. Sleeve bearings can work really well, um, and they're not as noisy as a ball bearing. Um, Sleeve bearings can work really well, and they're quieter than a ball bearing, but um, they do have their limitations. Um, if the load is going to windmill, so a condenser fan motor that's failed will windmill a lot. If you've got a big cooling tower, um, if you've got a big cooling tower with a fan on the side of it or something like that, what do you call those? That cooling tower design. If you got a situation where the fan's going to windmill, then that generally you want a ball bearing in that situation. So if it's going to spin at a slow speed, what happens is it doesn't keep the bearing lubricated. And since it doesn't keep the bearing lubricated, you're more likely to have issues. So a fan with a sleeve bearing, you really only want it to spin when you're going to tell it to spin. Okay? If it's going to spin from random wind currents and things like that, then a ball bearing is a better choice. Other than that, you can substitute ball bearing motors for sleeve bearings if noise is not a concern. Okay, so if you're not worried about the extra noise from a ball bearing, you can go with ball bearings instead of sleeve bearings. But if you're going to replace a ball bearing motor, it should be a ball bearing motor. All right, because there's a reason the ball bearing is part of the design. Sleeve bearings under normal operating conditions will last as long or longer than ball bearings. And then they give you some bearing temperatures and expected lives and ball bearing temperatures and expected lives. So you can see at 104 degrees, the sleeve bearing can actually last a longer number of hours, right? The good thing about ball bearings is they're more serviceable than most sleeve bearings. You can actually relubricate them. You can have a nice thick grease in them, and they can have a really long life if they're taken care of. If they're not taken care of, they're going to fail just like anything else. Again, do not substitute ball bearing motors for sleeve bearing motors if noise is a problem. So if you're using a sleeve bearing on an indoor unit and it runs pretty quiet, then you might not want to switch that to the ball bearing because it might be a little bit louder than before. use ball bearing motors in high temperature applications. If there's a chance that the fan will windmill, use a ball bearing motor. The other thing a ball bearing motor is good for is if you're going to use those variable speed condenser, high pressure condenser, low ambient controls. Okay, so if you got a low ambient control and it's just not an on off low ambient that you see put in, you can go to like Airco or something and get one of those ones that vary the speed. Those things are really hard on motors, and you don't want to use a sleeve bearing motor for that application because it'll lock up in no time because it won't stay lubricated when it runs at a lower speed. A lot of our motors can handle, running at that reduced voltage if you set everything up right, but you really want to use a ball bearing motor in that instance and not a sleeve bearing motor. Thermal protectors are built into the motor. Most of them are going to be auto reset overload. If it's manual reset, it's not going to be built into the motor. You don't see that very often. You see it on older compressors sometimes, but you don't see it on our other motors. You will see it in commercial applications now and then. Um, I've never across a one-shot thermal reset that was built in or anything like that. So overload protection is built in most motors nowadays. Trip and reset cycling of the thermal protection. All right. So if the motor's shutting off and then coming back on, and then shutting off and coming back on, that's one of the most common application problems for both PSC and shaded pole motors. It generally indicates overheating of the motor due to misapplication. So if you're seeing a motor that's cutting off on overload a lot, it means that somebody probably put the wrong motor in there, and you need to try and figure out what the proper motor is. Usually one of these conditions exists. The motor is overloaded. Amp draw is more than 10% greater than the nameplate amps. So if you're drawing more than 10% over nameplate amps on a motor, it's overloaded. It's probably too small of a motor. The motor is underloaded. Amp draw would be 25% less than nameplate. And don't get caught up in the weeds. This doesn't really apply to compressors a whole lot. It can, but it's not as important a factor. On compressors, it's more important to look at the entire situation and the uh, manufacturer's recommendations on as far as where amperage should be under certain conditions, because they go under a lot of different loads. But as far as blower motors and things like that are concerned, if your amp draw is more than 25% and less than the nameplate, that motor is probably too big for what it's doing. So you probably should have put a smaller motor in there. And amp draw being too low is just as much of a problem as amp draw being too high. You want that motor to stay loaded. And that's why, if you ever notice, most of your condenser fans and things like that, they're almost dead on nameplate amps. They're designed so that they run basically at full rated load, so that they're turning quick. They're doing enough work that they're staying lubricated and they're happy, and they're not doing so much work that they're over amping. So they're usually very closely sized. Little pumps and fractional horsepower motors and things like that are generally sized very close to what they should do. So could be a defective or incorrectly sized capacitors being used. And that can be difficult information to find, again, on something like a compressor, but generally on blower motors and things like that, condenser fan motors, it's right on the side of the motor. So if it's one thing that's relatively easy to check, is what size capacitor that motor should have. If not, you can try sizes close around it. You know what I mean? If there's a 7.5 in there, you can try a 5 and try a 10 and see if that helps it out, smooth something out a little bit. Um, Capacitors don't have to be super close on these things, really, but at the same time, you want one that's good for the application, and the capacitor size for a motor can change based on the application. It's not something that's always set in stone with the motor itself. So sometimes it doesn't hurt to try a different size capacitor if it looks like it's overheating a lot. 9 times out of 10, it's just going to be a bad cap. But you see weird stuff out there sometimes. All right, replacement motor has less ventilation than the original motor. So if you put a totally enclosed fan motor inside of a blower housing in a unit, that motor may not stay cool because of how the airstream goes around it. So you can't just switch out a motor with different ventilation. Temporarily, it's probably not a big deal if you're in a pinch and that'll work, but you don't want to leave a motor with different ventilation in an application. You basically want to give that motor as much ventilation as you can safely give it, given its working environment. High ambient temperature and/or exposure to the sun are a couple reasons the trip time can be shortened. And I made a little note here. A lot of condenser motors on rooftops should be rated 60 degrees C or greater. The inside of the supply house or whatever, when you're looking at motors, you'll see them rated for 40C, 50C, 60C, things like that. Especially if you're doing an older rooftop unit or something like that, where it's the environment's starting to get pretty harsh for that motor. The condenser's not in the same shape it was brand new. Especially if you're dealing with a black roof or something like that, where it can get really hot on the roof. You want to pick a motor with the greatest temperature rating you can to try and give that thing the best opportunity to survive. So those motors, pick a good robust motor when you're putting it on a rooftop condenser, because those things, even when selected halfway properly, they fail all the time. So you want a good robust motor on a rooftop unit. It doesn't hurt to upgrade uh, the um, the original design of the motor. That doesn't mean pick a different horsepower. That means pick one that's built a little more sturdy than the one that was before it. Condition 1 and 2 from above can be confirmed checking the amp draw. Condition 3, defective or wrong size capacitor will cause a motor to act as if it is overloaded. It will run slow, hot, and draw more than the nameplate amps. If all else checks okay, condition 4 suggests the application receive a motor with similar ventilation as the original. Do not bypass or jump thermal protectors to eliminate nuisance trips. I can't think of anybody who would have the gall to reach into a motor and cut that overload out anyway. You're more likely to mess up the winding than you are to jump out that thermal protector. But if you want to, more power to you. That thing's going to fail in no time. Okay. Lubrication. This goes through the different lubricating systems of basically your sleeve bearing motors. It says for routine maintenance and improved bearing life expectancy, a few drops of non-detergent 20 weight oil can be added every 12 months. If you want to be extremely thorough and do that on systems, more power to you. It's not that easy to get to those bearings to add that oil. It's not the hardest thing in the world. It's going to take you probably a good uh, 10, 15 minutes, including however much time it takes to get the motor out from where it's at. So most people don't add any extra oil, but it can actually be done. Just because it says it's permanently lubricated doesn't mean you can't add lubrication to it. You can do that and extend the life of a motor. It's just the cost usually don't outweigh the benefits. Ball bearing uses special greases. You should always use the ball bearing grease that's recommended by the manufacturer for those bearings. Um, I have a guide on greasing bearings. I'll try and pull that up for you guys and send it to you. Um, see if I can remember to do that. But yeah, if I don't, remind me someday. Hey, greasing bearings guide. There's a really good guide on greasing bearings. I can't remember who makes it, but yeah. All right. Capacitors. Always discharge a capacitor for removing it. Usually, a capacitor will be discharged by the time you go to remove it because it will discharge itself through the windings. But if the windings are bad, it will not discharge itself. So, you're supposed to use a high value resistor across it. Just ever so carefully stick your screwdriver across the terminals and you'll be fine. But turn off the power and discharge the capacitor before you take it out just to be safe. Usually you'll never get that spark, but if you do get that spark, you saved yourself a shock. So always discharge your capacitor. Um, if necessarily, so capacitors are rated by both capacity, how many microfarads, and the voltage, 370 volt or 440 volt. You can always use a 440 for a 370, but you can't use a 370 for a 440. If you've never actually measured voltage at a capacitor, and you got a 240 volt condenser, the voltage at that capacitor is probably going to be about 340, 350 volts. So the reason they're rated for 370 volts is because it gets up to 370 volts. So the reason they're rated for 440 volts is because it may get up to 440 volts. So it needs to be rated for that. So just like most other things, overrating it is fine, underrating it is not. Capacitors can be hooked up in parallel to increase capacity. For example, 2 microfarad 370 volt capacitors connected in parallel are equivalent to 10 microfarad 370 volt capacitors. See illustration below. So if these would be your lines going to your fan right here. All right. You connect these up in parallel. That's how you put 2 capacitors together. You do not put them in series. Do we have a picture in series? Maybe we don't. It's not really worth it most of the time trying to figure out how to hook up a capacitor in series to make a weird value. So I would basically just forget hooking up capacitors in series unless you really want to know all your stuff. Just don't even worry about it. If you need to add values together, you can do that by connecting them in parallel. If you got a 10 but you need a 7.5, you should probably go buy a 7.5. It'll be a lot easier than trying to hook up a couple in series to get a 7.5 capacitor. Capacitor life is about 60,000 hours continuous operation at rated voltage and maximum case temperature of 70 degrees. So, you know what, guys? You have to give me one more second. Then maybe we can go through a couple questions. Hold on just a second. Longer than an LED, you say. I don't know what capacitors you've been working on, but I think that 60,000 is very generous for most of your cheap capacitors out there. Right. Yeah. I don't know, man. It seemed like for a while there when they first started switching everything to LEDs, um, those things would fail really. Well, no, maybe I'm thinking of the fluorescents, the compact fluorescents. Anyway, when we stopped moving away from regular light bulbs, it seemed like everything failed quicker than the damn regular light bulbs did. But they've been doing pretty good lately. Um, all right. How do you tell if a motor is overloaded if the nameplate is unreadable? It's a good question. So you've got 2 ways to read the nameplate usually, right? If you're working on a piece of equipment, you've got the information listed on the piece of equipment on the nameplate of the equipment itself. Then you have the nameplate of the motor listed. If the motor nameplate is that unreadable, usually what I find, I don't know what you guys see a lot. Usually what I see is by the point that nameplate is unreadable, one of 2 things is true. That motor has either been overheating like hell anyway, and it probably needs replaced, and you need to make sure that the new one works relatively well in the application. And if necessary, you need to call a manufacturer to find out what the proper motor was for that application. Or it's so old the bearings are probably dying anyway. So I don't think you're going to be too worried most of the time if it's overloaded when you can't read the nameplate. Doesn't mean you couldn't run into that situation, but they're going to be pretty few and far between. But yeah, basically, you have no idea. There are some. You could probably. I don't know if there's one in this book. I don't really look for things like that too often. So we'll see if we find one. there is some guidelines on amperages to amperages, but I don't know if they give you horsepower to amperage or anything like that. Um, it's something I can look into. I don't know if there's a standard guide that says a 3/4 horse motor should be around X number of amps, but then you would still need to know the horsepower of the motor. So I don't know. Highlights on the test. Oh, where this is highlighted? And probably not, because this is not out of the book. So right now, we're not going until a couple classes from now. We're not going through any of this stuff that is going on your test. I promise you, we will go over what you need out of your book for your test. But right now, I'm just trying to give you more practical stuff in these next couple classes. So we're gonna cover stuff for your test as we get closer to your next test. Now, your test next week, you should have the stuff from the first class where I told you what to highlight. And if not, that video, I believe, is on YouTube, right? So you can watch it again if you need to re-highlight. And then we're gonna double check. We're gonna talk about three-phase near the end. But the short answer to your question, anyway, is you look at the direction it's spinning and whether or not it's spinning the right way. If it's not spinning the right way, you need to switch 2 leads. But on a compressor, it's not that easy. I guess we can talk about it now. On a compressor, it's not that easy, right? On a scroll compressor, a reciprocating compressor can't turn the wrong way. Everybody understands that, right? A three-phase reciprocating compressor has pistons that go up and down. So if the motor spins the wrong way on a three-phase reciprocating compressor, the piston goes up first instead of going down first, but it doesn't matter. It's still just going to move up and down. It doesn't change anything on a reset. On a scroll, here's what you want to do most of the time, okay? If you think the system might, if you're just starting up a system or something like that and it's three-phase, what you want to do is lock out everything, take the Y terminals off, off your thermostat wire, or disconnect the lead to the contactors for the compressor, or whatever you got to do. Okay. Just leave those things off so compressor won't come on when you first start it up. Let the fan come on and then see if the fan's spinning the right way. If the indoor blower for that unit is not spinning in the correct direction, or the condenser fans aren't spinning in the correct direction, flip both the leads, then let the compressor come on. And there you've made sure that the phases are correct. Fair warning, I have seen compressors wired backwards from the damn factory to where the blower is spinning the correct direction and the compressor is not. I've only seen it a couple times, but I have seen it. I don't know much. You basically got two options for a little over $100. Amprobe, I think it is. I believe it's Amprobe makes a phase uh, phase checker that you can hook up to the wires and figure out if it's in phase or out of phase. I've never used one. I can't tell you anything about them, but there is a product out there. Your next option would be an oscilloscope. I've never used one for that application. I don't know how to give you any practical knowledge on it. My best suggestion is to listen to the scroll, and if you know how a scroll is supposed to sound, you will be able to tell when that thing's running out of phase. And if you're not sure how it's supposed to sound, hook up your gauges. If the phase isn't hooked up right and it's spinning backwards, then it'll sound like shit and it won't pump. So if you're not sure how to listen for a scroll compressor that's wired backwards, then watch the pressures on the compressor to make sure it's not wired out of phase. And that way, if it's not pumping, immediately turn it off, switch 2 wires, and see if it pumps. That'll usually tell you for sure that you're in phase. If it's damaged, if something's wrong with it, it's not gonna pump in either direction, so it's not gonna matter a whole lot. But the scroll compressor wired out of phase is significantly louder than one that is in phase. A scroll compressor out of phase sounds a lot like a scroll compressor chewing liquid, or that is running under extremely high head pressure, and it doesn't do anything as far as pumping. So that's how you tell whether or not it's out of phase. As far as spinning the right way, obviously you should look for the rotation on your blower wheel to see which way it's supposed to rotate. And then on your condenser fans, I have never seen a system yet, doesn't mean it's not out there, but I have not seen one that is supposed to pull air in to the condenser on your standard systems. So it should blow up and out. It shouldn't suck down and in. If it's sucking down and in, it's spinning the wrong way. All right. So capacitor life about 60,000 hours. Continuous operation, much shorter on hot days. Really hot days will kill caps. Heat is what kills capacitors 9.5 times out of 10. So quality capacitors, AMRADs or something like that will help a lot. And making sure that everything's clean so it's not running too hot. If everything's pulling a lot of amperage and everything's real hot around that system, a capacitor is going to die quickly. So that's why you see a lot of capacitors fail on hot days. Hot days are what kills caps. Otherwise, caps last a really long time. You don't see too many failed capacitors on inducer motors and rooftops because those things don't get real hot because it's cold as heck outside when they're working. So, replace a capacitor when replacing a defective motor. In general, if you're replacing a motor, you should be replacing the capacitor and the contactor or relay. Now, if it's a solid state relay or one built on the board, maybe it's not worth it. But if your fan's hooked up to a contactor, if you're replacing that fan, replace the contactor, replace the cap. Just do it all at once so you're not back in a week. There are two safe ways to test capacitors in the field. There's actually three with a capacitor under load test. I don't know if we've covered capacitor under load test, but we will talk about that when we talk about testing capacitors themselves, which isn't a very large subject. It'll be grouped in with everything else, but we'll go through that. But you can use a capacitor tester. You can use an ohm meter and just make sure it's not short or open, or you can do a test with the capacitor under load, which is kind of my favorite. I'll usually do capacitor under load, and if I've got any concerns, also pull it out and check it with the meter and then go from there. But I prefer not to take them out unless I have a concern because, you forget to put them back in or you get a wire hooked up, messed up or something stupid. It's just one more thing to just avoid any extra steps unless necessary. Never do more than you have to. Always check a capacitor before replacing a PSC motor. Obviously, you should not replace a motor unless you've checked the cap, because if the cap's no good, the motor's not going to work. So it doesn't matter. You don't know whether it should work or not. And you can test the windings. If there's an issue with the winding or the bearings, then obviously you can tell. But in general, you always check the capacitor is one of the first things you check, besides whether or not it spins. A motor with a shorted capacitor can still start and run, but will operate as if seriously overloaded. So basically, the start winding is going to get power, but without the benefit of the capacitor limiting the current through the start winding. So if you actually have a shorted capacitor, which I can't say I've ran across, but it's a possibility that you have a shorted capacitor. If you have a shorted capacitor, it is possible that that motor runs. Not necessarily, but it's possible that that motor runs, but it will draw very high amperage because there'll be too much current through the start winding. This just tells you how to discharge a cap. All right, series connection. They do give you the information on series connection here. Again, I would ignore this. There's the formula. If you really want to use series connection capacitors, if you really want to use capacitors connected in series, be my guest. It can be done. You can hook it up so that everything works right, and you can use two capacitors that are a different size. Again, something like 2 5s will give you 2.5. So you could theoretically hook 2 5s in series with 1 5 in parallel with those two, and you would get a 7.5 microfarad cap. In my mind, you end up with so many capacitors making up the bank of them, probably not worth your time messing around with it. If you're really in a pinch, It's nice information to know. It's easy to find online if you really need it. I would not commit this to memory for anything. You should commit to memory doing parallel connections, and that's pretty easy. Capacitor 1 plus capacitor 2 plus capacitor 3, yada yada. You get to just add them all up when they're in parallel. Condensation and drain plugs, very important, very commonly overlooked. All right. If you got especially an outdoor motor, condenser motor, two things can happen. You can get rain in somehow, right? You know, if there's water getting in, you can get water ingress into the motor. But the other thing that happens is it's not totally enclosed. It's not like this thing is sealed off with silicone, okay? Air still gets in and outside the internal case of this, well, the internal section of the motor from outside the case. So differences between daytime and nighttime temperatures create condensate in totally enclosed motors, and a drain hole should be at the lowest point in the motor to prevent condensate water to exit. And remember, we were talking about shaft up, shaft down, not that important because most things can be done either way. Well, there's a drain plug on both sides. And it seems like it's become a lot more common for them to just pull out the bottom one for the shaft down and assume that's the position and then expect you to move the drain plug to the other side if it is shaft up. But a lot of motors still come with plugs in both drain holes. Pull the plug for the condensate drain on the totally enclosed motor. If you don't pull the plug, the motor will probably short one day because it's going to build up condensate inside of it. The water is going to hold in there pretty good, and it's either going to deteriorate bearings or it's eventually going to deteriorate the windings enough or build up enough that you create a short in between the windings. So it's very important to remember when you're doing a totally enclosed motor, figure out where the drain plug is and make sure it's out. It's always going to have a drain plug somewhere. Make sure you pull it. Be sure to pull the condensation plug on the motor on the end that will point down. Fasco has two colors of plugs on the motors. The blue plugs are condensate plugs and the yellow plugs are for re-oiling. Other manufacturers' drain plugs are generally black. But yeah, there are re-oiling plugs in some motors, but you don't see them that often. Generally, if you see a plug, it's probably a drain plug, unless we're talking about a pump for like a boiler or something that commonly has a motor fill port. Motor stacks and winding. A motor of the same diameter and stack can be substituted when either horsepower or ampere rating of the defective motor is known. The stack of a motor is the width of the stator iron laminations. So, if you are in a situation where you have no idea what the horsepower of a motor is that you need to replace, if you pull the motor and you take it apart, and I thought there was a picture in here, right? Yep. All right. So if you pull the motor and you take it apart, here's your stator. The stator stays in place and gets electricity. The rotor rotates, right? So the rotor is what's on the shaft. That's what's attached to the shaft. And that spins while it's standing inside the stator. You see these laminations right here? On the inside, these are your stator laminations. The width of these laminations can tell you, it can give you a good idea of what the horsepower is. So if you find a motor that has similar laminations, that's how you can determine which motor you use. You may never use this information, but it's interesting, right? I would say it's probably easier to call up the manufacturer and figure that out. It's not that often these days that people want seriously old equipment like that repaired where you've got to take a shot in the dark and figure something like this out. But who knows? Little stuff like that always saves someone's butt. So maybe that'll save your butt one day. That is one way to try and figure out what the horsepower or power output of a motor basically is. Most open circuits and windings, so if you have an open winding, okay, on a motor, resulting from defects in the motor windings occur within the first 2 hours of operation. That means that if you have an open winding and that motor's been operating for more than a day or so, it probably wasn't defective. Something else was wrong. Just something to keep in mind. Something went wrong. It probably wasn't the motor being defective. So if you have that situation, you might want to make sure you pick the right motor, or whoever was before you picked the right motor, or whatever. Um, the It's just something to understand. 90% of failures are related to installation, right? So you should always assume somebody did something wrong, not that the part was defective. Doesn't mean you won't get defective parts, but that is not your baseline attitude. Your baseline attitude is, okay, how'd it get fucked up? Okay. Your baseline attitude is, who did something wrong to make this fail? And then if you say, well, nobody did anything wrong, I've checked everything and everything's right, then you can say, well, part was made on a Friday. It's no good. Toss it in the trash, get another one, it'll be fine. So, most short circuits and windings occur if motor windings are wet within the motor when the motor is operating. Remember, pull your drain plug. So that's where your shorts come from, or if lightning strikes. Usually, shorts are not a result of motor overheating since the motor is thermally protected, right? How are you going to get a short in a winding? Short in a winding is generally going to occur when the motor overheats, the insulation breaks down, and then you get two windings, two parts of the winding touching each other, right? That's hard to happen though because the motors are thermally protected. So you're more likely to get an open winding because it's going to have some catastrophic failure than you are a shorted winding. And a lot of times open windings, again, this is just an experience thing. It may be a lot less true than what I think it is, but in my experience, usually an open winding ends up being due to a bad bearing. You have bad bearings, something fails mechanically, and then it fails electrically. It usually does not go the other way. Doesn't mean it doesn't happen, because it does. I've seen it happen, but it usually is the mechanical failure precedes the electrical failure. All right. I just highlighted this to make sure I brought up efficiency. Again, PSC motors, you're usually talking somewhere around 60% efficient. So anything, any of that efficiency that's lost, right? So if you're doing a 100-watt motor, 50 watts of that is probably going to be heat that you have to dissipate from the motor. There's a lot of heat that motors create that you got to get away from it. There's so much heat that we include it in our load calculations. Okay, so when you do a load calculation, you add the heat of the blower to the cooling load of the house, because you don't only have to cool the house, you have to cool the blower motor. And sometimes that's 1,000 watts. It's not a ton, but it's 1 kW of heat that you have to get rid of. So you need to take that into account with your load calculation. So it's not a huge amount, but it's not a trivial amount either. All right. So there's a lot of heat to get away from a PSC, or especially a shaded pole motor. All right, shaded pole is least efficient. It's half as efficient as a PSC, generally about 30%. All right, when replacing motors, it's best to match the motor type, but you can use a PSC instead of a shaded pole. You cannot use a shaded pole instead of a PSC. That's a bad idea. Use a PSC to replace a shaded pole. Cool. Use a shaded pole to replace this PSC. No, because it's going to draw more amps. And you don't know if the rest of the circuit was made for those extra amps. And it's going to be less efficient, which is never a good thing, right? Multi-speed motors are less efficient than single speed motors due to space limitations for the windings. So something to keep in mind. Um, Depending on the application, if you started with a multi-speed motor, but you know what speed that motor needs to run on and what the horsepower needs to be based on that speed, because most multi-speed motors are really multi-horsepower, not multi-speed. Okay, so if you know you got a 3/4 horsepower maximum multi-speed motor and you've got to run it on high speed all the time, the system would be more efficient if you just replace it with a single speed 3/4 horsepower motor of the same RPM. Done. So just something to keep in mind. Multi-speed motors where they're not necessary is actually not a very good idea. It's just it's a convenience thing more than anything else, because nobody cares that much about fractional horsepower motors anyway. the difference in energy lost isn't huge. But if you're trying to eke every bit of it that you can out, just going multi-speed to single speed could save you a little bit of efficiency. All right, an overloaded motor is one that is too weak for the job. Its speed will be low. Its amp draw is more than 10% above the nameplate rating, and it will have increased heat rise. Its motor life will be reduced. An underloaded motor is one that's too strong for the job. Using too strong a motor for replacement is evident when its amperage draw is 25% less than the nameplate reading. Using a motor with excessive horsepower can also cause increased heat rise due to decreased efficiency. Overmotoring an application increases RPM very little. And we're going to talk about this a little bit more near the end. But in general, if the fan's not coming up to speed, increasing the horsepower is probably not going to get it up to speed more. There's probably something else wrong that you need to fix. There are very few situations, especially talking residential, where it's like, well, it's got a half horse blower in it, so maybe if we put a 3/4 horse blower, we'll get more air out. No, it doesn't work out quite that easy. So you can forget that idea. Now, in commercial, belt drive versus direct drive, low static to medium static systems, you can make a big difference going to the medium static blower design. So if you had airflow problems and it had a low static RTU, you can go to a medium static RTU and probably get better performance. But that's a lot more than just changing the motor. So maybe we get into that at some point. Maybe we don't. If you have questions on what I just said, let me know in a little bit and we can discuss it a little bit more. Make a note for us to go over it. But yeah, you're usually not going to increase speed by increasing horsepower. All right, in most cases, RPM for a 6-pole motor designed to operate at 1,075 RPM would only increase by 50 RPM if the motor's power was doubled. So if you had a half horsepower motor and you were running at 1,025 RPM and you want to get to 1,075 RPM, you need a 1 horsepower motor. That's how hard it is to eke that last little bit out when you've got a design issue. Some energy efficient motors will have matching horsepower but lower amps. In general, if you know the motor's more efficient, you can expect it to draw lower amps, but it's kind of rare, except on 3-phase, that you're going to make some kind of crazy jump in efficiency. So in general, matching amps is easier than matching horsepower with motors. It's not something we do by default, but it's something we should do more often, is match amps, not necessarily horsepower, because there's a lot of deviation in how these manufacturers rate their horsepower. It's gotten a lot better than it was, years and years ago, but it's still, they still try and sell you a 1 horsepower motor as a 3/4 super heavy duty. All right. Horsepower is the usual measurement of power output. Horsepower requirements vary with the cube of the speed and air moving applications. We're going to talk about this more when we get down to it. But this is a very important thing to understand, but it's hard to understand reading it. In other words, replacing a 6-pole motor with a 4-pole motor requires a 4-pole motor that has 3 times greater horsepower. It's not fun. It's hard to just change poles out. You always want to use the same number of poles. Basically, if the old motor was 1,800 RPM, you want an 1,800 RPM motor. It'll be 1,750 or whatever, but you want the same RPMs. You don't want to try and make up that speed some other way. All right, when replacing motors, the horsepower of the defective and replacing motor should be the same. If motors rated below 1/4 horsepower when horsepower rating is not available, matching the current rating is a satisfactory procedure. Do not use a replacement motor whose nameplate ampere rating is less than the defective motor. The replacement motor may have nameplate amps 25% greater than the nameplate amps of the defective motor. All right, load factor is how much extra horsepower a motor can put out. Load factor is not service factor. I don't see load factor used very much in day-to-day, but that's what load factor is. So, load factor is basically an overrated motor. Again, this is a quarter horsepower motor that's actually a third horse. So it's got a whatever percent load factor, 1.3 load factor. So it basically just means it's actually got more horsepower than it says it does. And that was a very common thing with motors for a while. Tough application, for example, is where an OEM used a marginally designed motor with just enough horsepower to get by. So what they're basically saying is if you've got an issue where the motor just barely handles the application, then having a motor with a higher load factor will enable you to have that motor last a little bit longer. Um, Basically, you just end up going up a notch in horsepower, essentially. It's not much different than doing that anyway. And when we're talking fractional horsepower, one notch isn't a whole lot. Half to third, third to half, half to three quarter. Usually it's not going to be as big as we make it seem in here, but, you know. All right, 5 5/8 or 5.6 inches. We talked about that. When modifying a motor shaft, make certain the shaft is tightly held in a vise to avoid stress on the motor bearings. I recommend a bandsaw or a grinder. You will probably not have a good day using a sawzall to cut a motor shaft. It can be done. I would not recommend it. Bandsaws and grinders tend to do it cleaner without putting stress on the bearings. So if you got to cut a motor shaft, consider using one of those two tools before taking the sawzall out, or even the hacksaw for that matter. But they recommend holding it in a vise to make sure you don't put stress on the motor bearings. If you're going to use a sawzall, you might want to put it in a vise. It's up to you. It always sucks putting in a brand new motor where you messed up the shaft, though. When cutting a shaft to length, it is extremely important to prevent steel filings or shavings from entering the motor. You don't want those things getting into the windings, because they're just going to sit there, rust, eat stuff away, cause some kind of problem in the windings. Make sure there's no metal burrs left on the shaft after it's cut. That is just to make your life easy, really. It's hard to get a fan blade on a motor with a dicked up shaft. All right. This is interesting. I was reading this again because I probably read this book once a year, and I never really paid much attention to this. But it says there are a few common ways contractors shorten a motor through bolts. So when the bolts are too long coming out of the motor, there's a few ways contractors do it. Typically, I'll be honest, I use a crappy pair of dikes that I'm not worried about messing up, or a bandsaw. All right. But they say whether they snap them off with a hollow nut driver or cut them off with small bolt cutters. I guess you take the nut driver, put it over the, you take the hollow nut driver, put it over the threads, and then I shouldn't be too hard to just snap it off, but I've never tried it. So if you have, you can speak up. But it's an interesting thought on how to shorten those bolts. But I've never seen anybody do it. Anyways, it's always a good idea to first spin on an extra nut all the way down to the face of the motor. They say that it's so if you keep reading, they talk about you can, after you put that extra nut on, snap off the bolt, you can remove that extra nut so that you can later take the motor apart. I actually wouldn't worry about that so much, as those rods, those through bolts are really thin, and if you over tighten them or something, you can really mess up the alignment in that motor. So I would recommend putting that extra nut down on the through bolt, just so that you can try and make sure that through bolt doesn't move. Because especially if you're going to be snapping them off with a nut driver, it doesn't take that much effort to bend that through bolt. And once it's bent, trust me, I have done it before. It's not a fun day trying to get a motor back into alignment where you've over torqued a bolt or something. I've done that once, and I've never done it again, because that motor sounds like crap until you get it all lined up again just right. So don't over tighten the through bolts, and don't mess them up or get them bent, because it can throw that whole thing out of whack. There's not a whole lot of clearance between your stator and your rotor. The base speed of a motor is determined by the number of poles. The number of wound coils in the motor equals the number of poles. So the more poles you have in the motor, the slower it turns. And the more poles, the more expensive it is to make. So typically you're going to see a lot of 4-pole motors, a lot of 2-pole motors. And then you get into some 6 poles. You don't see that many 8 poles out there, but they exist too. But you always want to have the same number of poles, and you'll know that if you're matching motor speed. All right, multi-speed motors will only indicate speed variations when loaded. When run without a load, a motor will run at a single unchanging speed. So I don't know if you've ever done this, but I've seen it done. If you take a multi-horsepower motor, right, and you put it in, and you got it on high speed, it runs at full speed. And you're like, well, it's too much, right? You take it down a notch to medium speed or medium high, right? It'll run at the same speed. Means you still have too much horsepower. You take it down to medium low speed, it still runs the same speed, which means you still have too much horsepower. And then you take it to low and you actually get a somewhat lower speed. But I've actually seen a motor so oversized for an application like really short duct runs. You know, you've got very little duct off the equipment, so there's not much resistance to air. And so that 3/4 horsepower motor from the factory or half horse or whatever it is runs at full speed even on low speed because you don't have enough load to slow the motor down. You're trying to load down the motor to slow it by removing horsepower basically, and it just doesn't happen. So, you know, at that point you may have to go down a horsepower in the motor design to get that lower speed that you need. It does occur. You know, they can only design for so many variables. You've got a minimum and a maximum amount of duct, like for instance on an air handler, that motor can deal with. If you just got no duct on it or very little, the motor's probably oversized for the application at that point because it's not made for that situation. All right. Hmm. Modern multi-speed motors are really not multi-speed, but multi-horsepower. We've kind of went over that a few times so far, but that is what the case is. Remember, the motor relies on the load to slow it down between the speeds. As an example, if a half horsepower 3-speed motor is used instead of a 1/4 horsepower 3-speed, there may not be any noticeable difference between high, medium, and low. Here they talk about a nameplate reading 1350 RPM. I've never seen that, but if you do, there's a uh, big note in here. The nameplate showing 1350 RPM is a special design and it has to be replaced with that exact motor. It's a high slip 4-pole motor, which is generally not available in a general line of motors. If one is available, it would be marketed as an OEM direct replacement motor for a specific piece of equipment. These motors are specially designed for a very specific load. So if you ever see a 1350 RPM motor, get another 1350 RPM motor. You probably got to get it straight from the manufacturer, and they're probably going to charge you triple what it's worth. All right. Talking about multi-speed motors again. If it's a 3rd horsepower multi-speed, it's going to be 3rd horsepower on high speed, 1/4 horsepower medium, and 6th horsepower on low. So basically, that's what we do with those multi-speed motors is we're just grouping horsepower ratings together. And that's why if you look on the side of the multi-speed motor boxes, you'll see it says 3/4 replaces 3/4, half, 1/3, and whatever 1/5 horsepower motors or 1/4 horsepower motors or whatever. It gives you the horsepower ratings that those speeds essentially are on the side of the box. Add picture. I don't know why. Of permanent split and shaded poles, but we'll kind of see what those look like. Okay, here you go. Number of poles in normal to high speed. If you got 2 poles, it's 3,200 RPM. You got 4 poles, it's 1,650 RPM. Usually, really, it's 1,725 is what I see most of the time. So, 2 poles is 3,200. 4 poles, it's really like, let me redo this. A 2-pole motor is theoretically 3,600 RPM, but it's usually going to be after slip in the motor, it's going to be closer to 3,250 RPM. 4-pole motor is theoretically 1,800 RPM, but after slip in the motor, it's going to be closer to 1,700 RPM. 6-pole motor is theoretically 1,200 RPM, right? 16. Yeah, 1,200 RPM. I want to say it's usually going to be 1150. And an 8-pole motor is theoretically 900 RPM. It's going to be 850. So that's how your poles work out to speeds. So that's basically all you got to remember. You'll get used to those RPM values and you replace it with one with the same RPM value. And then they talk about those high slip motors again. Saying stick with the original RPM and horsepower because it's talking about replacing one of those high slip motors. So we're not going to go read all that, but use the right RPM and horsepower of a motor. Rating motors with BTUs. The following helpful guides have been successfully used to approximate the motor horsepower based on BTU rating of window air conditioners. This is for cases where the motor nameplate has no horsepower listed. So if you have no idea the horsepower of the motor you need, there's a little chart here based on the BTUs of a window air conditioner, what size motor horsepower you need for the condenser, and I assume the blower too. And then they give you a list for central AC system condenser fan motors. So if you're unsure, up to 7.5 tons, this is basically, you can approximate your condenser fan motors like this. If it's different on the original manufacturer, use the original manufacturer. But if you have no idea, this is probably close because size of coils and everything is what's going to dictate this, and BTUs is going to dictate size of coils. So this is probably pretty accurate, but I haven't looked at this chart, then looked at a unit, then looked at this chart, then looked at a unit. So I can't tell you for sure if this has stayed accurate or how old it is and how long they've been using it, but this probably works. So if you ever need that information or you ever need to guesstimate, it's a nice little chart to have in the back of your head, I guess. Motors are cooled by the way that they're cooled, and make sure that they're cooled. Replacement motors often need, for outdoor condenser fans, may require a rain shield. So if you do need a rain shield, depending on the type of motor and how it's replaced, you need something to keep the rain from getting onto it, you can buy rain shields for your motors and put them on. Motor temperature. Overheating is a sign of an overloaded or underloaded motor. A motor winding can typically get to 100 degrees C. When you see that 60 C rating on a motor, that's the ambient temperature rating. The rating inside the motor the temperature inside the motor is going to be much higher than the ambient temperature. So a 60 C motor is made to be in a 60 C ambient environment. But the inside of that motor starts to reach boiling in the environment that it was rated to be in. Heat's the primary enemy of motors. Excessive heat is a sign of misapplication, or it shortens installation life and dries out the bearing lubrication system, causes the overload to trip. A 40C motor is rated for 104-degree ambient. That is not enough for a condenser motor, especially if it's on a roof. 40C motors should not be used for condensers. So if you do that, it's a bad idea. 50C motors are rated for 122 degrees. That's a little bit better, but it's really not enough. A 60C motor is rated for 140 degrees. That's why I say generally use a 60C motor, especially for rooftops on condenser fans. That's what you want. Then if you really want to go out and get you a 70C motor from somewhere that can handle 158, that's even better. Heat and moisture are the two most important factors limiting motor life. Moisture can be the result of rain or condensing of warm moisture inside the motor. Water can collect in a motor without drain holes at the lowest point, and if the coils are touched by this water, a ground or short can occur. Underpowered replacement is more likely to cause problems than overpowering. If the motor is too small, it will usually be worse than a motor that's too big, but both are bad. This is just a long diatribe on making sure that you replace a condenser motor. Use the same type of motor because it's really hard for you to guesstimate what that motor needs to be, even though they give you a chart earlier in the book. But if at all possible, always replace motors with the exact same as the design unless you know better. Speed controls. If you're going to put a speed control in a motor, did that start up here? Hold on. No, it just goes on the bottom. So on condenser motors, speed controls, the result of either a specific speed control must be tested with a specific motor. There are no general lines of speed controls that can be used across the motor offering. Each motor will respond differently. So when you do an aftermarket speed controller, you basically have to take your best shot at picking a suitable motor. Generally, if you're going to use a speed controller, I'm going to say use a high temperature rated ball bearing motor with about the right horsepower and see how it works out. That's usually going to be your best shot at not having issues using a speed control aftermarket. Even then, you may make a mistake and be replacing that motor in a year if you make bad choices. But usually, if you do that, you're fine. If you use a weak, off the shelf, $60 sleeve bearing motor on a speed controller, it's probably going to fail. All right. It is advisable to place thermocouples in the windings to monitor the motor's operating temperature throughout the speed range before using one of these controls, and you'll generally want a ball bearing motor. So if you really want to make sure that the motor's okay with the speed controller, you have to get some thermocouples that you can put inside the motor, something that can read those thermocouples, so a good meter, and you need to monitor the temperature to make sure it doesn't reach, over 100 C. Clockwise and counterclockwise rotation drives me insane. It drives me insane because no motor manufacturer is the same. So you have to pay attention to what it says the rotation is on the motor. It's going to say clockwise or counterclockwise shaft end, or it's going to say clockwise or counterclockwise lead end. So if you're looking at the lead end, if it says it's clockwise lead end, you'll be looking at the lead end where the wire leads are, and it's going to spin clockwise looking at the leads. So if you turn it around and look at the shaft, and you're looking at the shaft end, it's going to spin counterclockwise on the shaft. All right, and every single one of them labels it differently. I think that's why we have so many reversible rotation motors, even though they're almost always spinning in the proper rotation when you throw them in. Okay. It's pretty rare you got to switch that rotation, at least in my experience. Okay. They generally spin the right direction. But you can never tell for sure which way to set that damn rotation, because that you'll say the motor says clockwise, this motor says clockwise, and then it's spinning the wrong way because one said from the shaft end, one said from the lead end. So anyway, the best method is to scratch a rotation arrow on the motor before removal. I would probably use a marker instead of scratching it. Do what you want to do, but you should probably put a rotation arrow on the old motor so that you can make sure that the new motor is set right. It's not a bad idea. Can't say I've ever actually had to do it. There's probably one or two times I wish I would have, but not enough for me to go crazy. All right, this is all the information you need when replacing a motor. In general, voltage, number of phases, horsepower, frame size, diameter of the motor, RPM, and bearing type is usually enough. If you've got all those pieces of information, 7 pieces of information, if you've got all that, that's all you generally need to replace a motor. A lot of times, not even that much. But if you're trying to put the same motor back in, that's usually your best choice on, or your most important pieces of information to get another suitable motor. Selecting too strong a motor will also cause overheating, as if we haven't said that a million times. But this is basically a guideline on, what's the amps of the defective motor, what the amp should be for your replacement. So, I mean, it's basically up to 25% over, you know what I mean? 5 is 5 to 6.25 amps is correct. I don't know if you really need a table. Don't go over more than 25% over the original amps, but you want to be as close to the original as possible with all other things being equal. And there's a table there if it helps, though. Matching amp rating is usually more precise than matching horsepower. Speed and voltage of the replacement motor must always match speed and voltage of the replaced motor. A PSC motor can replace a shaded pole, but not vice versa. We've already talked about that. The table below will help with this procedure. Motor selection verification. It's the same stuff again. Amps, safe amp range. Motor wiring and rotation reversing. All right. Motor wiring. Typical wiring for shaded pole motors is black. Usually doesn't matter which way you hook up the wires. Depending on how it's designed, it may run in the opposite direction, but I don't think that's very common. You just hook up your 2 power wires and your ground and you're good to go. Interesting note that I don't think they mention in this a whole lot. A lot of times for our applications, the ground is actually not necessarily, because we're usually mounted to something metal, which means the motor's already grounded and you don't need the extra ground. But always connect your ground anyway. It's pretty common practice. It's not like a lot of people aren't connecting your grounds, but generally for our applications, the ground is actually not that big of a deal. Just get it connected so it looks good and it's neat. But I mean, and then if you have multi-speeds on a shaded pole, you'll want to connect the lines. I think this will come up again, but you can never ever have 2 speeds running at the same time. It does not work. It will kill the motor. Okay? So you can only have power connected to 1 speed at a time. On a PSC motor, typically you're going to have a brown with a white mark. Then you're going to have a black wire. And then white is common. Sometimes white is yellow. Yellow is common instead of white. But the brown with the white mark just ties on to this white wire internally. If you open up the motor, this brown wire, all right, this thing right here is just wire nutted essentially. It's just got a little clamp on it that hooks right to this wire. They're the exact same wire. The brown wire, we're going to look at a diagram to help it make it more clear. But the brown wire goes to your start winding, your auxiliary winding, and then this wire just goes to this one. You don't need it, which is why you see a lot of 3-wire condenser fan motors. This is basically just a dummy wire so you don't mess it up. And then if you have multiple speeds, then you obviously will connect the line to 1 speed at a time, just like any other multi-speed motor. All right. The ground wire is there. It'll be green or green with the yellow tracer. Grounds are always green or green and yellow. That's common with everything. If the original motor does not have 2 separate capacitor leads and the original wiring pattern is desired, the following wiring diagram can be used on many Fasco motors. The following wiring diagram can be used on almost any multi-speed motor. So if you're trying to replace a 3-wire condenser fan motor with a multi-speed condenser fan motor, and you don't have the wire going to, you don't have the wire that goes to brown and white, you know what I mean? That brown and white wire sitting out there to grab on, the capacitor's 5 compartments away, and you need to hook up the capacitor again, and you don't want to stretch a 10-foot wire out. All you have to do is put brown on one side of the cap, tape off the brown with the white mark, put your common line to the other side of the capacitor, and then take the common line to power. All right. All you really need is the brown, the common line, and the black line. And I'll tell you why I hate the fact that we call this common here in a little bit, because it's not really common, but it really is common. It's confusing. But anyway, your white wire or your yellow wire is on the exact same. It basically looks like this inside this motor. All right. Dadgummit. Basically looks like this. right inside this motor. So this brown with white wire just ties right onto that wire inside the motor. You just don't see it. So this is just so you don't mess up wiring a capacitor wire, because this makes sure you can't screw it up and accidentally connect the brown to line. If you connect the brown to line, you will have a problem. Otherwise, you do not need this wire right here. Just wire nut it off. You can, I just thought this was interesting. This is just for fun facts, okay? It is theoretically possible, if you need to reverse a motor, that you can mechanically reverse it, but you have to remove the stator and turn it around. I don't know if you can do the same removing the rotor and turning it around. It doesn't tell you you can do that. Removing the stator is all but impossible. I've never seen a motor where it was easy to take the stator out. So I have no idea what motor you're going to have that you can take the stator out, unless somebody knows how to tear down a motor better than I do. But if you can get the stator out, you can theoretically reverse a motor by doing it. If line voltage is applied to two speed leads at once, the motor winding will quickly overheat and fail. The overload cannot protect the motor in that case. You're basically screwed. If you connect two speeds to power at the same time, you will kill the motor. You will need a new motor. That's one thing that I actually didn't know for a while. I always thought, okay, what happens if you connect two speeds at once? I mean, if you think about it logically, you've basically shortened the winding a ton, and you're basically just going to overheat it. So it should make perfect sense that you can't connect power to both at the same time. But sometimes those things aren't as intuitive as they seem. So that is the obvious choice, is that you can't do it. But this is the first place I ever actually read in plain English that you can't do it. So anyway, you shouldn't carry a motor by the leads. If it's the old motor, go ahead. If it's the new motor, don't do it. They're basically just held on with Kapton tape on the inside. So if you carry it by the leads, if all it has to do is that lead slips, and you're going to tear out that really fine motor winding. So don't carry it by the leads. Again, never connect line voltage to two speed leads. In fact, one brown capacitor lead on Fasco's motors that has two brown capacitor leads has a white tracer. Tape off this lead if only one capacitor lead is required. Simply connect the solid brown lead to one side of the capacitor. The other side of the capacitor is where the motor's white wire lead is connected, along with one of the AC power leads. Just like I showed you on that picture, and just like we'll look at again when we look at some diagrams real fast. All right, motor installation. Here's some interesting stuff on motor installation. If you've never installed one, maybe you want to read through this on your own time. We're not going to go through it together, but you should. If you don't do much installation of motors, that might be an interesting thing to read through. Mounting of motors, same things. It should be mounted the way it was originally mounted. I can't think of many applications where you guys are going to be designing the mounting and the design of the motor on your own. It's generally replacement, and it should generally be very similar to how it was before. Blower motors should have some kind of rubber grommets on them. So if you're going to change the mounting bracket on the motor, you want to pick one that's similar and has some kind of vibration isolation. You know, if it's mounted like this with these grommets, then you want to mount the new one like this with these grommets. You know, don't redesign the world mounting a motor. Just do it the way it was before. Again, unless you want to get super into all kinds of stuff that is not necessary to know. Make sure you pick the right contactor. Contactor should have the same ratings or better. So I mean, if the contactor is rated for 30 amps and you only have one rated for 40 amps, okay, fine. If the contactor is rated for 40 amps and you only have one rated for 30 amps, probably not fine. Induced draft blowers, it goes through a section on that. Generally, you're going to be buying OEM equipment at that point. A lot of times these things are hard to get apart, so you end up buying the whole assembly. That's my pro tip if you don't do a lot of induced draft motors. If you're unsure, the motor's failed, but everything looks like it's 15 years old, buy the whole assembly It'll save you some time. Sometimes this stuff is a nightmare to get apart. So it's usually easier to buy the whole assembly if you're unsure how difficult the process of removal is going to be. If you have a blower wheel, if it's impossible to determine the motor rotation, the fan blade can be used. Hold the fan blade in a horizontal position, hub up. All right. So this is going to be pointing up. Hold it in that position, pointing up. If the fan blade curves to the left, you need a clockwise rotation based on how they do it. I can't remember, shaft end or whatever. It turns clockwise, okay? Lead end, sorry. And it's counterclockwise when looking at the shaft of the motor, okay? So if the fan blades curve down, then you need a clockwise motor, because if the fan blades are curving down, it needs to spin this way, because the next highlighted portion says, and it's true, the cups of the blower fins push the air, and that is the direction of rotation. So those cups on your blower wheel, all right, hopefully, I don't know if I'm in frame. Let me check if I'm in frame. All right. The cups of the blower wheel push the air like that. All right. So if you were ever unsure, never paid much attention, or going to end up in a situation where you don't know, don't get me wrong. Some things are different. You can have pump impellers where it pushes the water like this. All right. There are large commercial designs where the fan pushes the air like this. There's a train guide on different blower designs that I go through sometimes. So maybe we end up looking at one day, maybe we don't. But for most residential light commercial blower wheels, the cups push the air. Okay. So there you go. If you were ever not sure, hopefully now you're sure. All right. An increase in static pressure can be caused by a clogged furnace filter. This will make the blower unload and increase in speed, but deliver less air. This generally results in less air over the motor for cooling, and the motor will also draw less amps. Say it with me. If you reduce the airflow, then you increase speed but reduce amperage, and you run less air. Okay? So as a motor gets overloaded, what happens is it gets across this point in this curve where it's just going to run at full speed, but it really doesn't do anything because it can't do any work. It's got to do so much work that it can't do any work. You're basically deadheading the fan. If you deadhead the fan, if you had a main damper at the top of your unit on a residential unit, or or commercial air handler, it doesn't matter. If you had one big damper that could cut off all the airflow, if you cut off all the airflow, the amps on the blower will drop, and it won't deliver any air, but it will overheat. That's not important on pumps most of the time. It is important on blower motors. But the point is that if you try to make it do more work than it can, it just won't do any work. But it'll run full RPM because it's just spinning free, basically. It's not doing anything. So there's no work it can do, so it doesn't do any work. So the amps go down, and it just doesn't deliver any air. So try and remember this for me. It'll come up again when we talk about hydronics. If you deadhead a fan or you deadhead a pump, amps go down. Air output in a furnace cannot be increased by just changing motor speed. Air output on an air handler cannot be increased just by changing motor speed. It's not that easy. There's a lot of factors that go in how much air a system can deliver. It's not just as easy as making the fan spin faster. Theoretically, you'll get a little bit more air if it's spinning faster, but the odds of you getting it spinning fast enough that it does that is actually pretty small unless you know what you're doing. So, and that's the next thing I think we go over. The fan laws. All right. We're going to simplify the fan laws real fast. All right. We're going to simplify these fan laws real quick. Hopefully, we do a class on airflow. There's so many things I like to go over. I can't always get them all in. Hopefully, we do a class on airflow and fan laws. We'll at least do basic class on it. I always don't go deep into fan laws. I always try to make sure I do. Sometimes it just doesn't make it in the curriculum. If it's in the book, it'll make it in the curriculum. If it's not in the book, it may or may not. But the 3 laws that you need to understand is that if you want a new CFM, okay, then the new CFM divided by the old CFM equals the new speed divided by the old speed. Okay, so you have to increase the speed proportionally to get the new CFM. The new static pressure that you're going to get is divided by the old static pressure, and that equals the new speed divided by the old speed squared. So your static pressure goes up by the second power of the old static pressure. That's significant. We're going to see an example in a second. The new horsepower divided by the old horsepower is going to be the new speed, or the new horsepower by the old horsepower is going to be the new speed divided by the old speed cubed. So the new horsepower is going to be to the third power of the old horsepower. So let's look at an example. Hopefully it makes more sense. All right. If we had a system where we had 5,000 CFM, but we wanted 9,000 CFM, so that we had 5, but we want 9, what's going to happen? Well, if the old speed was 450, the new speed has to be 810. So we have to double our CFM base. Because we're almost doubling our CFM, we have to almost double our RPM. Okay, doesn't sound like too big of a deal, right? Sure, it's not too big of a deal. But what about your static pressure? Well, your old static pressure was a 1/2 inch water column. Your new static pressure is going to be 1.62 inches of water column. So that's basically, just like I said, going from a low static system to a medium static system. You're going to a system that was designed to run to under 1 inch of water column to one that's designed to run under 2 inches of water column. You're tripling your static pressure by doubling your CFM. And then when we get to the horsepower, your old horsepower was a 1/2 horsepower, and now you need a 3 horsepower motor. It's not that easy to just double your CFM. Even 1.5 times your CFM, you're making it tricky. Maybe if you want 25% more, you can make it work, okay? But when you start to say, oh, I need double the amount of airflow, there's situations where I've even seen engineers are like, oh, well, we just need a bigger motor. Okay, do you know how much of a bigger motor? You think we can fit it in the equipment? Do you know how much extra static pressure that motor has to work against? The duct isn't designed for it. Okay. You want to remember these, not like remember them like you should remember them off the top of your head, but you want to remember how difficult it is to make this happen. Okay? Because this is pretty difficult to do. You are usually better off buying a system that's designed for the new CFM than trying to make an existing system work like this. The only exception being certain situations with exhaust fans, you can use this to your advantage. But if you're talking about heating and cooling systems, I mean, forget about it. You're losing your mind. There's so many other things that are going to change. You're probably screwed. You know, if you bought a low static unit designed to work at 0.5 inches water column, and you should have bought a medium static, you're not going to be able to get that low static to work. You need a belt drive, RTU, or whatever to make it work. That's why when you order those things, a lot of times they're like, well, what static do you have to work at? Because if you need it to work at 3, they can sell you a system that'll work at 3 inches of water column if that's what you need. But you can't make the one that was made for 2 inch of water column work with 3 inches of water column. It's not that easy. A lot of times you're changing out more than just a motor. You're changing out shivs, maybe the fan wheel, the motor, half the air box, and even then it might not work. So there you go. There's your fan laws. The most important part of your fan laws, how quick all that stuff goes up. So this example shows that an 80% increase in airflow requires a 480% increase in horsepower. Careful consideration should be given to any changes in air moving equipment to assure results are accurate and practical with practical being the primary note right there. You want it to be practical. And then we just get into the glossary. I highlighted clockwise versus counterclockwise, shaft end versus lead end, and I think that's it. So that is my favorite permanent split capacitor motor guide. I've looked over it, like I said, every year for years. I always teach it in class because I really like their Fasco motor guide. So I wanted to go through the ECM service guide, but it's almost 8 o'clock, so I don't think we're going to do that. Before we leave, though, I do want to go over internal windings. So these are my pretty little pictures of internal windings. Let me make sure it's actually popping up. Yep. All right, these are my pretty little pictures of internal windings, and I went through a reasonable amount of effort to make these damn things, so enjoy it. It's a pain in the ass making sure I got some of these things right because the motors don't work the way you think they work based on the way that we generally talk. All right. And I'll explain to you what that means when we get to PSCs for like compressors and condensers. So a shaded pole motor, you have a main winding and then you have a shaded pole. And this is a thick copper wire that are around the poles. So if you have a 2-pole motor, you have 2 shaded poles. If you have a 4-pole motor, you have 4 shaded poles. This would be a 1-pole motor. You probably won't have a 1-pole motor, but I just show 1 shaded pole for reference. Maybe I'll add another one in there so it's a little bit more accurate. But that's how a shaded pole motor is set up. So this winding isn't tied on to anything. It's just there to the magnetic field induces a current in the shaded pole, which ensures that the motor rotates. Shaded pole motor is always single phase, 30% efficient. It's a single winding. All right. Permanent split capacitor. Dang it. All right. Permanent split capacitor. These are your 2 basic permanent split capacitor motors. Here's the funny thing. I've got these things color coded, okay? So the yellow would be your white. This would be your brown and white if you had one. This is your brown. And then this is your speed. Your motor overload, your common wire, okay? The one that ties on to R and S, run and start. The common wire is really your speed wire, okay? The black wire is your common wire. Even though we call this yellow wire our common, that's tied directly into our run winding. And then our brown wire is tied directly into our start winding. And then the one that ties onto both windings is your speed winding, and that's where your overload is located. Okay? This is a 3-wire configuration. We're just tied right onto the white wire, right? This brown and white goes over and ties on the same side of the contactor as that yellow wire. Usually there's a jumper from here to the same side of the contactor as your yellow wire or your white wire, okay? So if you pay attention to how these things are wired on your systems, these 2 wires go together no matter what. If you have 4 wires, so you have a brown and white wire coming out of the motor, like I showed you before, it's just tied on right there on the winding. It's just tied together inside the motor. So no matter if you tie it together inside the motor or outside the motor. All you got to do is move this white wire to this side of the cap and jump it to power. No matter how you do it, it's just both of these wires, one side of the capacitor and this has to be tied on to L2 or L1 or whatever. This brown wire cannot connect to power. You cannot have this connected without a capacitor. If this connects to power without a capacitor, what a capacitor does on a motor is it limits the amount of current that can be used by the start winding. So if you connect it directly to power, you're going to allow it whatever current it can handle through there. And whatever current it can handle is enough to kill it. So you do not want your brown wire to ever touch main power by itself. The brown and white, it doesn't matter, but it does need to be the same as your common wire. But the common wire is kind of the black wire if you think about it. Depends on what you consider common. So it's really hard to decide which one's which, right? It's hard to decide which one do I call common. but in common parlance, the way we talk about motors and the way manufacturers label them, this white one is the common one, okay? If that doesn't make sense, I'm sorry. Just pay attention to the picture. Know that this is common. This is your capacitor wire, your start winding, and this is your speed tap. All right. So a permanent split capacitor motor, 3-wire top or 4-wire bottom. You can wire it either way. It is 60% efficient. The start winding and the run, you have a start winding and a run winding. So you have 2 windings, right? Start or auxiliary and run. Start. If you want to measure start, you go from your brown wire, to your black wire. That will give you the resistance of this start winding. So you'll be measuring resistance from here, through your start winding. Run is black to common. So your speed tap or whatever it is to your common wire. And obviously, well, not so obviously, you don't want the capacitor in the circuit when you're measuring the resistance. Okay. But going black to white or yellow will give you run. Going black to brown or start will give you that. And going brown to white without them being connected, right? Because they shouldn't be. The brown with white can connect to white, but the brown cannot connect to white. Going brown to white is going to give you the resistance of run and start put together. So start plus run should equal start and run. This resistance plus this resistance should equal this resistance. It's not going to be 100% accurate. You're not going to get in down to 0.2 ohms or something, but it should be relatively close. The heat of the windings, if the motor's been running recently, if it's been sitting still for a long time, all those things are going to affect this winding temperature. There's a lot of copper in there. So that winding temperature is going to affect how much resistance there is. But it should be somewhat close if you put those together. If it's not, if you get 12 ohms in, if you get 12 ohms and 12 ohms in 1 ohm, then you've got a short somewhere, okay? If you get something wildly out of whack, you probably have a short. Now, one thing to keep in mind when we say that, though, is if you have a multi-speed motor, it gets a little tricky. So if you have a multi-speed permanent split capacitor motor, you don't ever see it done, but you can still wire those 3-wire, just like we showed in the Fasco facts. So just keep that in mind. If you're in a pinch, you can wire a multi-speed motor 3-wire, no big deal. Everything is the same as a single speed permanent split capacitor motor, except for what I've encountered is that the formula here seems to work best if you're measuring high speed. So all these speeds are just taps in this winding. So instead of having a long winding, we have the tap right here that's high, and that's the shortest amount of the winding, okay? So the tap right here on high uses the least amount of winding, and it has the most horsepower because it has the least resistance for the voltage to travel through. Sort of like if you had a less resistance in an electric heater, it's a similar concept, even though inductive loads and resistive loads are different. If you've got less resistance, more power, okay? Medium high is going to use a little bit more of the winding, on and on. Low uses the full run winding, all right? So the full length of that winding gets used when you got that motor on low. The overload is placed on the high speed tap because all of the high speeds have to go, all the lower speeds have to go through that section of winding that the high speed tap is on. So since it's got to go through that section, no matter what speed you choose, they place the overload on the high speed tap. So that's where this is located. The start winding is actually tied in, from what I've seen, is generally tied in right by the high speed tap. So that's where the run and start get tied together, is over here, not down here. All right. So if you're doing this formula to figure out if this motor's good, which you're probably not going to do very often, to be honest anyway, we use this formula more often to check compressors. But if you're just having fun and you're testing these things out, this does generally still work. but it generally works if you're using the high-speed tap. The entire length of this winding could be similar to your start winding. So, if you measure, if start's 43 ohms, run might be 43 ohms if you measure it if you measure it red to white. That might still be 43 ohms. That run winding gets longer than the start winding, or as long as the start winding. But in general, the start winding is usually like 3 times more than your run. So just keep that in mind. It's not really necessary anyway. Generally, what you're going to do is say, is this winding open or shorted? Is this winding open or shorted? Is my overload open or closed? Because usually the overload's going to be what opens. And if these overloads trip enough, it's just a little bimetallic switch basically in there that curves and bends with heat. So if it opens enough, it likes to get stuck open. Overloads really like getting stuck open, which is why you're having an issue with like a compressor or something. You want to try and get that thing to stop overheating as quick as you can, because enough cycles of opening that overload and it's not going to close next time. So anyway, if you're going to use that formula, in my experience, using high speed works. The other interesting thing about multi-speed motors, okay, especially if they're a little bit oversized. So say you use a multi-speed motor that can handle up to a 1/2 horsepower, but you really only needed a 1/3. Okay, so you might be using the medium-high winding at that point. If the motor fails at medium-high speed, high still might work, because high uses less of the winding than medium high. So sometimes a multi-speed motor will still work on a higher speed, but no longer at a lower speed. So sometimes you can get yourself out of a pinch, or get somebody out of a pinch, by switching it from low to high for a minute. So like if the furnace, low speed fails on a furnace, and because you're using low speed for heat, if you turn the fan on, the fan might run and they can keep heat until you can get a new motor that works on low speed. Does that make sense? It's a good way to get temporary air moving just by switching to a higher speed. Sometimes the higher speed taps will work when the lowers don't. But if high speed doesn't work, none of them will work. ECM and three-phase. Three-phase motors are pretty simple, and I never put L1, L2, L3 on here. So the nice thing about ECM motors is you troubleshoot them exactly the same as a 3-speed motor. If you've never taken an ECM apart, if you're going to test the motor windings in the ECM motor, what they do with the ECMs is they basically, not really, but you might as well just say they basically convert single phase into 3-phase in an ECM motor. So the ECM motors have the same winding configuration as a 3-phase motor. 3-phase motors are 75 to 90% efficient. They have 3 equal windings. All windings should have very similar amperage and resistance. L1, if you read from L1 to L2, and L2 to L3, and L3 to L1, you should get the same number. If you take the control module off an ECM motor, there's a little plug right there where you can measure the windings, and you should get 1 to 2, same as 2 to 3, same as 1 to 3. It's as simple as that. If there's anything more than a couple percentage points out, something's probably wrong. If you read 10, 10, 5, that motor's no good. If you read 10, 10, 9, it might be all right. I wouldn't throw it out without testing it to power. But if you're reading something insanely different from the other windings, then it's probably no good. Odds are you're tripping breakers and stuff anyway when that happens. The other important thing that I didn't note here on 3-phase motors is you can't single phase them. So if you've never heard that term, if you only have L1 hooked up on a 3-phase motor, so L1 has power, all right, so this one is powered. Let me just highlight it for fun. If L1 is powered, okay, So this has power going to it, but L2 and L3 do not. You're fine. Nothing bad's going to happen. If L1 and L2, all right. If L1 and L2 have powered, but L3 does not, this motor will draw amperage. It will try to run, but it will not be able to run. It's only going to be going, power is only going to be really be flowing through 2 windings, okay? It's going to try to rotate, but it's not going to be able to, and the whole thing's going to burn up. If you got overloads, the overloads might save you. Usually breakers will save you because it's going to draw really high amps. But if they don't, if none of that ends up saving it, these windings will just open. They'll just overheat and fail. So you always have to have either one phase of one line of power on, or all 3 lines of power on. You cannot have 2. 2 lines of power is what is single phasing a 3-phase motor, and it'll get you. The other thing about 3-phase is this is a delta configuration. This is a Y configuration. They can be set up in either depending on the application and the voltage. Sometimes you can use it delta for a high voltage and Y for low voltage, especially in Europe. It's not that important for practicality, no matter how you do it. If you do L1 to L2, L2 to L3, L1 to L3, you'll still get the same resistance. So troubleshooting wise, it's not really important. Even practical application, it really doesn't matter if it's set up for Y or delta. You just want to make sure that you've got the same motor if you replace it. You should always be careful with 3-phase motors to get one that's substantially similar. And that's all I got.